Hi, I'm Derrel Martin. I'm a professor in Irrigation and Water Resource Engineering here at the University of Nebraska. I'm in the Department of Biological Systems Engineering. I want to visit with you a little bit here about managing soil water to achieve our goal. In order to really operate an irrigation system so that we achieve the yields that we need to have, but also protect the water resources from the groundwater pollution, we need to really think about how we manage this water. And so we're going to do a quick overlook at some of the concepts and what goes into managing that soil water. What we're really about in irrigation is trying to manage the soil water here in the root zone, that stored soil water, keeping it in a range where we doesn't lead to a lot of deep percolation on this side, but it's also still adequate in order to supply the evaporation and the transpiration that the crop's going to need. Now, the decisions we make, of course, affect how much irrigation water we would apply into that system. And so a lot of what we're looking at in soil water balance management is really keeping this root zone so that it's really at the right, in an appropriate range for water content. So this little diagram is trying to look then at the different ways that water is stored in the soil. And so what we look at to begin with is if the soil were completely saturated, every pore was filled, so it'd be like groundwater, we would be at the top of that box. On the other hand, at the bottom here, if every drop of water was gone from the soil, we'd put it in an oven and baked it for a couple of days. That really defines the range of the amount of water that soil could hold. But gravity has an impact on how much of the water stays in the root zone for the plants to use. And at the same time, plants cannot extract water from very dry soils. And so we end up with a narrow range here. So field capacity refers to that soil moisture content where the rate of water flowing out of the root zone due to drainage becomes a negligible rate. So a very small amount of water would percolate from the root zone over a period of days. So the key is that water that's between the field capacity and saturation, this water here, is water that's going to naturally drain from our system. So we can't really count on it being around when the crop needs the water. So we don't want to irrigate above this field capacity very much because that water is probably not going to stay in our root zone. The lower limit of what we have here is going to be the wilting point. So this is the moisture content where if the soil were left at that water content for a day or two, plants simply cannot extract that water from the soil. This water down in here in this unavailable area is water that's held very tightly in the soil pores, and plants just can't simply extract that water without paying a high price, either for yield or even maybe perhaps wilting. And so the water we have available to us to manage that we really want to manage with irrigation is between this field capacity and this wilting point. Now, some of that water, the top half of this water, this point of water here, is actually more readily available to the crop than that last half of the water there. The less available water that's shown in this diagram is water it's available to the plant, but the plant has to do quite a little work to extract that water from the soil, and you may start to see some impacts on yields as the plants exert that extra energy to extract that water. So what we really want to do is we want to keep this water here in this more available zone, a readily available water in this zone as we manage that soil water. So some characteristics that we have to think about then are that field capacity. This is that moisture content when all the water, excess drainage has become quite small due to drainage by gravity. The wilting point is where that's the very ultimate driest that we can achieve. And the amount of available water we have is really this difference between that field capacity and that wilting point. Now, these numbers vary a lot by different soil types. And so this is what we call a moisture release curve. So what we're showing on this axis here on the bottom, on the x-axis, is how tightly the soil is holding the water. So when the value is small, like say 0.1, then the water can easily flow in the soil and the plants can easily extract it. When we get down here to about 15 centibars, or 15 bars, this is the number that we refer to as the wilting point. That's about as dry as we can get and still allow plants to survive over a couple of days. So what we've shown here is for 6 different soil types, how these curves vary a great deal. We really can't, each soil is a little bit different as we go from a silty clay to the sand fine sand on the bottom, very rapid change in the way these soils behave. So we really need to know something about your local soil if we're going to try to manage that. The blue dots that are shown on each one of these soils is actually the field capacity estimate for that particular soil type that we're using in some of our management guidelines. And you can see those numbers kind of move around a little bit on this chart. And so you really need to have local information on how available that water is. Now, the amount of water available, let's just look at the silty clay. This number here is going to be the wilting point, and this number back up here is going to be the field capacity. So the available water is going to be this distance between the blue dot and the black dot for your respective soil. Again, the soil water tension down here in the bottom is showing how tightly the soil is holding that water. And we're going to talk about measuring that soil moisture tension, or how tightly the soil is holding the water in just a little bit. Well, there's a lot of data here, and so what we're showing is that each soil has some very unique characteristics. We're looking at the surface soil, the subsoil, and maybe even this lower horizon here back on the side. And so we're looking at, we have data here, kind of representative data for a bunch of soil types across the state of Nebraska. And again, it's going to be critical that we kind of know what soil type you have in order to be able to manage that water reservoir. How do we go about measuring that water? We certainly can't manage what we don't measure, and so we need to have some way of knowing where we're at in that system. So we're going to talk a little bit about whether it's field methods, sensors, and how we're going to go about measuring this soil water to kind of tell us where we're at. You can think about this as maybe like a gas gauge, so maybe we can put some systems in the field and we can monitor how full your gas gauge is or your water tank is for the crops to use water. The easiest of these methods is the method we call the field method. What we really do is go out and take a sample of soil with a probe like shown on the lower left here. We take that soil sample, we put it in our hands, and we kind of try to make it ribbon out. We kind of form a ball and see how solid that ball is. And so we look to see how wet we think the soil is by judgment. Now there's a good guide here that you can go to and get some nice pictures to give you an indication of how dry the soil is by soil type. What we find out is that this method is very good because it's very inexpensive. It lets you look around the field and see what the variability is in the field. If you're going to get good at this, you really need a lot of practice, and you need to compare yourself to something that is a standard. And so we really encourage people to still be doing the field method. A lot of times we get pretty busy and we aren't able to get out there in the field. The other thing we find is a lot of times people don't want to do the work to get down to 4 feet with this system, so maybe they only do that top 18 inches. And it's pretty important for us, especially for water quality, to look at what's going on in the bottom half of our root zone. So this was a good method, but it just kind of is too much work for some things today. Another method is we can go in and measure the soil water potential. So here's a tensiometer. This is a system that we're showing here is a Watermark sensor. Both of these devices measure how tightly the water is held by the soil. So we can get an indication here then of how closely that water is held. And if we have a graph like we saw a little bit ago with those 6 soils, then we can also look at how much water is in the soil for each one of those soil types. And so we do that in various ways. We have several different tools that you can utilize to take a look at that for your soil type. These methods are very popular. The Watermark has become quite popular. Kind of varies in price. This is somewhere in the $30 for this particular type of sensor. Tensiometers can be very good, but they're a lot of work to maintain. You have to go out and add water to them periodically, and so a lot of growers are probably going to shy away from these unless you're on really sandy soil, but I don't see many people interested in the tensiometer. This you can hook up to an electronic system, get a reading, make a judgment, and don't have to do much maintenance once you've installed those. There's an example of some tensiometers on the left, and here's some Watermark sensors. What we do is we take this sensor that's here and we glue this onto a piece of PVC pipe so we can insert this in the ground, and then we label those as to their depth in the field. And so now then, in this case, we're right in the row with those devices. And so, put a good flag out here so that you can find these. So these are easy to go up to. We have a little device you can measure these with if you want to do it out in the field, and it's pretty easy to do. So, here we might be showing that there's actually 4 sensors here, only seeing 3. This is probably $120, maybe a little bit more for this type of installation. And we've used these sensors for many years, 5, 6, 7, 8 years. We still have sensors we're using. So this is a really pretty low investment cost after a period of time. The average cost per year is pretty low. Ways that you can read those, the handheld methods that are shown there in the middle of that meter, all you do is they take those 2 alligator clips, you clip them onto the leads that are shown on the moisture block on the left, and you get a reading right in your hand when you're there. We also are using some devices that we call data loggers that are shown down here on the bottom. And what these devices do is they read these blocks about every 15 minutes and they record that in a data logger system. And then you can go out, and it kind of varies by how you do it. The data logger on the left, you can push a button and you can see what the water pattern was over 35 days for each sensor. The one in the middle there is made by the Watermark aerometer people that make the Watermark. And so what you do is you bring the leads into this device, and so it records the data for you. You can go out in the field and walk through those numbers or download them onto a computer or some iPod or something like that. We're also beginning to see more interest in a wireless technology. This is available in a lot of different formats. This is actually a little older generation of that technology by Aerometer. The problem we have today in Nebraska, though, is most of our land's irrigated with pivots, and in order for this wireless technology like this to work, we have to have clear line of sight. And we're not able to get these devices up so that they can have a clear line of sight and not be interfered with by the pivot. So we're looking at different ways of being able to maybe bury some wire and get this equipment here out of the field, and then you can get up high enough that it doesn't interfere with the pivot. We've done that in several locations. It seems to work pretty well, but we're looking at different ways to make it available. What we hear from growers is that they want this data to be available to them when they're in the field, and they also want to be able to access that on the internet or through a wireless connection to be able to look at their data maybe when they're planning things back in the office. So it's become pretty critical for people to be able to do both of those. Of course, with today's smartphone technology, you may be able to get the internet from about anywhere. But people want the ability to see it local when they're in the field and also use it from a workshop someplace where they're making plans. This is a pattern then that we might look at over time. This happens to be 2007 when we did this work. We have 4 sensors, as you can see here. These sensors are 1, 2, 3, and 4 feet. What's shown on the left is what we call a watermark reading. Now what this means here is the larger that reading is, the drier the soil would be. And so you can see this top line here, this blue line is the 1 foot line. It's very dynamic, it moves up and down. When it rains or it irrigates, it's probably going to go above field capacity. That water is going to percolate through the upper level down into the lower levels. As we look over the season, if we were to look at this green line here, that really represents the 3 foot line. And this pattern kind of shows what we like to look at here. The green line's getting a little bit drier as we go through the season, so we're able to extract a little of that water so that we leave the root zone drier at the end of the season. And hopefully we can capture some rainfall and either during the fall or in the next spring before we need to irrigate again. By doing that, it really helps us minimize leaching of nitrogen during the non-growing season. And many times that's when a lot of our leaching occurs. The rains in the spring a lot of times are what drives some of that loss of nitrogen due to leaching in the springtime. So you can see these patterns. We like to look at these and kind of see what we're doing. We also like to define a range. Maybe there's a certain range here of these values you'd like to stay between. And there's no one absolute reading here that's critical, but we'd like to have you stay between kind of a list of values for your soil type. This is a little different kind of technology here. This is a capacitance type probe. There are a lot of different manufacturers of this. What this system is doing is really measuring how the water content in the soil affects the transmission of an electric current through the soil system itself. The drier it is, then there's a thing called a dielectric constant. The constant for water is quite big, and that affects the rate of speed of travel of a wave through the soil. So what we do with these is we might install these out in the field, the one that's shown here on the left, takes about an 1.5-inch diameter hole. We would go out and make that hole. Many times they'll add a slurry to that, and then they'll push this probe down into that hole. The installation of these is just critical. You have to get good contact between the probe that's shown on the left there and the soil. And so sometimes they'll use a slurry to get that contact. If you don't like the slurry, you might make a little bit smaller hole and force the staying in the ground so that you get good contact. This particular device has been connected with a solar panel. It has its own data logger there, and this particular device is communicating via satellite. So they're able to get this signal back out to a website about anywhere you're at. The data you get out of this particular design, this was if you wanted to look at each one of the sensor depths itself. In this case, you had 4, 8, 12, 20, and 36 inch locations that they were making readings. You can see those very shallow, the 4 and the 8 bounce up and down a lot. By the time I get down to 3 feet, now this is changing pretty slowly. You can kind of integrate all of those and look at a kind of a management strategy for your system. And so what this diagram here at the bottom is showing is this might be a full point, and down at the bottom might be a kind of a dry point that we'd want to get to. We want to irrigate before we get much of the field at this point. We'd like to not get wetter than this point up here with the full profile. This person did a really good job. Actually, this point where we go above, these little spikes here where we go above, those are primarily due to a rainy period in this particular location. It's a fairly sandy soil. And so, we were a day or so that we might have been above that limit. That water then percolated into the lower root zone, probably was used by the plant over that time period. So what we're looking at in this, as much as anything, is the pattern of this curve over time. What we'd like to see is that we're within an acceptable range, and we're kind of staying in that range over time. If we find out that our soil is getting wetter over time, well, that means we're probably irrigating a little too much. If it's getting drier over time, maybe I'm not putting enough on. So we encourage you to find a range and then try to manage so that we stay in the range. We don't need to make this too complicated. It doesn't have to be an exact specific number. Just find a good range and stay within that. The other important part in these systems is where would I install these devices? First of all, you got to put them in a location where you're going to go and read them. There's no point of putting them on the backside of the field that you can't get to. And so what we want to do is we want to look at the soils that might be represented. So this diagram is showing different soil types for this particular field. There happens to be a waterway shown by the arrows down to the middle there. We definitely wouldn't want to install those in that location. So maybe we'll find some locations in the field there that are kind of shown by the blue and red dots where we might want to think about locating those. If the field road's in from the north, in this case, well, we're probably going to put those kind of in those areas north of the pivot point. So find a soil and a slope that's representative, maybe a little bit drier conditions in your field, and then put those in those locations and monitor them periodically throughout the season. That's kind of what it boils down to. Some people prefer to put in some sensors, especially with furrow irrigation. You may choose to put some sensors in that are on the leading edge and then some sensors on the backside. So those, if the pivot's normally making a clockwise rotation, what you find on the left, those ones below the pivot to start with are areas that are irrigated first. That kind of tells us if we're letting it get too wet or too dry before we irrigate. These here on the backside are telling us is it getting too dry before we get there. And so we kind of want to look at those together and keep both of those areas within this range of acceptable water content. Not too hard to do with a pivot, a little bit harder to do with systems that you put on larger amounts of water and it takes longer to cross that field. So let's look at an example. Suppose we have a Hastings silt loam soil here. We have corn, it's maybe at the silking stage, and we put Watermark reading equipment in at 1, 2, and 3 feet. And our readings are 90, 80, and 80. Now those are centibars. That's how tightly the soil's holding the water. And we want to look at how much water is available to the crop and when do we need to begin irrigating. So what we do is there's a chart that's available from a NEB guide that's in the material. And so what we've done is looked at different soil types here. So each one of these columns is a different type of soil. On the left-hand axis there is the Watermark reading that you would get. And on this axis then is the amount of depletion of soil water that would occur for that soil type at that reading. Now what we had was readings at 80 and 90. The top one was 90 and the bottom two were both at 80. The Hastings silt loam is the third column of soil. So what we see with this system is that top foot would have a depletion of about 7/800ths of an inch of water. The lower two would have a depletion of about 7/10ths of an inch of water. So we can look at that then. So we had 7/800ths at the top. The next two were 7/800ths. And so what we see is we've used a total here of 2.18 inches of water we've used out of the profile between irrigations. Now if we back up here on this soil type, you see down here at the very bottom, you'll see that this soil holds about 2 inches of water, 2.2 inches of water, of available water per foot. That means the amount of water between field capacity and the wilting point is about 2.2 inches of water per foot of soil. So if we come back to our example now, if we had a root zone that's 3 feet deep, represented by these numbers, we see that the soil could hold a total of 6.6 inches of water in that 3-foot root zone. But we don't want to irrigate. We don't want to be in the bottom part of that. So the amount of water that we still have available is 4.2 inches, but we don't want to try to use that whole 4.2. We might want to try to irrigate when we've maybe used about 35% of this 6.6 inches. So we're probably just in a pretty good place right now, maybe to begin an irrigation in this case. We could let it get a little drier. We could maybe let it get down to about a little over 3 inches and still not have a problem. If you have a low capacity well, we like to see you irrigate a little bit earlier, keep a little bit of water in that soil so that you can make it through that week that's hot and dry, or if you have an equipment problem. We don't want you to be so wet though that if it rains you lose that water. So what we're looking at here is we've used 2.18. We could use about 3.3. We got a little while before we could need to irrigate, but as long as we don't put on over 2 inches of water, we could probably start today. So I guess just looking at this a different way, do we need to begin to irrigate? We can look at that. If each one of these sensors is the same depth, we can just average those numbers. So if we average 80, 80, and 90, that average turns out to be about 83 is our average matrix potential. Our trigger point for the silt loam is about 90 to 100. So we don't really need to irrigate yet. We could wait a little while to let it dry out. We also could probably irrigate now as long as we put on an inch of water or so, when we'd be in pretty good shape. If you want to look at more of this, we have a lot of information available. This is one of the early extension circulars that kind of describes some of this process. There's a website here for this program looking at some of our crop water use. And so we encourage you to go out and take a look at those resources to maybe fine-tune this to your location. Besides just monitoring soil water, we want you to think about a strategy. And so what we're looking at here is dates on the lower axis, and we're looking at inches of available water on the vertical axis. And so as the roots grow, we start off with a small amount, and we end up with about 6 inches of field capacity in this particular example. So it's sloping up because our root depth is growing during the growing season. So that would be the upper limit of where we would want to be with soil water. We would like to leave some water here in this, what we call the rainfall storage zone. We'd like to leave some water in that area so that we could store a rainfall event throughout the growing season. So if we're not so wet, then we can actually store that inch or so rainfall that comes along. What we really want to be, our desired zone, is this green zone. That's where we would like to stay within during our growing season. We don't really care where we're at here all that much. We just don't want to be on too high or too low. The red zone represents that area where stress begins. Now we show this increasing over the time early in the year because we have growing roots. We also increase it here in the middle part of the season. It's a little bit steeper here because that's a more sensitive time period. So we might want to keep the soil a little bit wetter during pollination. That's also when my ET rates are high, and so I want to make sure I don't fall behind. As I get to the latter part of the season here, we drop this back down. And so our goal is really to stay in this green zone. Now you can see this individual did a very nice job of staying within that zone. Early in the year, we might have been a little wet due to rainfall, but once we got into the irrigation season here, shown by these blue bars, we stayed very nicely in this green zone. We were also able to even, over time, we were able to drop this water level and actually create some storage in this root zone at the end of the growing season to store that precip so we don't leach nitrogen or we don't have to pump water next year. So So besides just monitoring, we want you to think about a strategy for how you manage those profiles over time. So this is our summary looking at soil water management, some thoughts for you, maybe ways to not over-irrigate but not stress the crop, minimize that percolation, and protect that groundwater quality.